I have 3 tuning forks of different frequencies, and this is a hard substance known as rubber pad on which the tuning fork, when hit, the prongs of the tuning fork start vibrating. The tuning forks are often marked with numbers. Like here it is marked as 128 Hertz. This number signifies the number of vibrations per second of the tuning fork. That means this one, which is marked as 128 Hertz, will vibrate. The prongs of this tuning fork will vibrate 128 times in 1 second. The second tuning fork is marked as 256 Hertz. That means the prong of this tuning fork will vibrate 256 times in 1 second. On the other hand, the third one is marked as 512 Hertz, which means that the prongs of this tuning fork or the tines of this tuning fork will vibrate 512 times in 1 second when hit on a hard surface. Okay? I will now hit these 3 tuning forks on this hard surface, and you should try to observe or listen to the sound that is produced by these 3 tuning forks. I have taken the tuning fork of frequency 128 Hertz. This is a plastic wrapper which I have taken. Now I'll hit this tuning fork on this hard surface, and I will make one of the tines touch this plastic wrapper. You should observe what happens once I make this tine touch with the wrapper. We can't see air molecules bouncing off of the fork, but we can see sound in water. For this, I have taken a bowl which is filled with water, I will take one tuning fork and I will hit it on this hard surface and then I will put it in water. Watch carefully. You will see some water that is shoot all over the place. Have noticed the splash of water that was formed during when this tine was made to touch with the surface of water. This splash pattern is similar to what happens in air. The speed of sound tells us the rate at which sound travels from the sound producing body, that means a vibrating body, to our ears. And the formula which has been taught to you is V equals to F lambda, where V stands for the speed of sound and F is the frequency and lambda is the wavelength of that wave. This is a general expression for the speed of sound. But when we have to calculate the speed of sound in a gaseous medium, then the formula is little different. Then the speed of sound is equal to under root of gamma p upon rho, where gamma is a constant which differs when the nature of the gas is different. P stands for pressure in the particular gas medium and rho is the density of the medium. We have experienced several times that during the rainy season, a flash of lightning is seen first and sound of thunder is heard a little later, although both occur at the same time. Therefore, we can say that sound takes more time to travel the same distance than light. And this is why the speed of now this is happening because the speed of light is much greater than speed of sound. There is one more application that we see. The gun is fired from a distance. We see that the flash of the gun first and then the gunshot is heard later. Also, in the game of cricket, the ball is seen to hit first and then the sound of hitting is heard. So all this concludes that the speed of sound is much less than the speed of light. Experimentally, it has been found that speed of sound depends upon a number of factors. The basic factor on which the speed of sound depend upon is the nature of the medium. This particular table shows you the approximate values of the speed of sound in different media. This table, the first table is for solids and the second table consists of liquid and gas medium. In the first table, you will see that the speed of sound is maximum in aluminium and minimum in vulcanized rubber. However, in liquids, the speed of sound is maximum in seawater. That means the sound travels fastest in seawater out of these four liquids. Similarly, in gases, the speed of sound is maximum in hydrogen and minimum in sulfur dioxide. These values have been found experimentally. The speed of sound, therefore, is seen to be maximum in solids and minimum in gases. And this is because the molecules are packed closer in solids and liquids than in air or gases. Hence, the molecules carry the vibrations and they do so more efficiently when they are closed together. The values which are shown to you here are the values of speed of sound in different medium or different media at 25 degrees Celsius. There are few applications also based on the different values of speed of sound in different media. Let's see what are those. A person presses his ears against a railway track to find whether a train is approaching or not. This is because we know that speed of sound is maximum in solids and minimum in gases or in air. The sound produced by the moving wheel of the train travels much faster through the steel track than through the air. So the sound is heard through the steel track before it is heard through the air. Similarly, there is one more very common application based on this concept, that two whales which are hundreds of kilometers away from each other can communicate easily through seawater. And this happens because you have seen just now in the table that the speed of sound is maximum in seawater. That means it travels fastest in seawater than in plain water, and that is why whales are able to communicate with each other easily. So these were some of the applications of different values of speed of sound in different media. We will now see different factors that affect the speed of sound in gas, only in gas. Okay. So there are different factors. Basically, there are four factors. First is the density of the gas, then temperature of the gas, humidity in that particular medium, and direction of the wind. We will go through one by one now. The first factor that affects the speed of sound in a gas is the density of that particular gas. According to the formula, which is meant only for the calculation of velocity of sound in a gaseous medium, V equals to gamma P upon rho. As I have said earlier, gamma is the constant of proportionality whose value depends upon the nature of the medium. P is the initial pressure of the gas and rho is the density of the gas. So from this formula, it can clearly be observed that velocity and density of the velocity of sound and density of the gas are inversely proportional. That means velocity or the speed of sound in a gas is inversely proportional to the square root of the density of the gas. And this implies that the denser the gas, the less is the speed of sound. And therefore, the velocity of sound in hydrogen is much more than the velocity of sound in oxygen. And this you have seen in the table as well. Let's see the calculations, the calculation related to this particular theory. The speed of sound is given by this particular formula. Therefore, for a given temperature, the pressure of hydrogen gas is same as the pressure of the oxygen gas. And gamma, as I have said earlier, is constant. So the density is, which is mass upon volume, when we'll take the ratio of velocity of hydrogen to the velocity of oxygen, we'll get this relationship, which is equal to under root of density of oxygen to the value of density of hydrogen. Now, when we will put the values of density, which is mass upon volume, what do we find here is that we will find that the velocity of hydrogen is actually 4 times the velocity of oxygen, velocity of sound in oxygen. And therefore, the greater the density of the gas, the lesser is the speed of the sound. The second factor that affects the speed of sound in a gas is the temperature of the gas. The speed of sound in a gas is directly proportional to the square root of the absolute temperature of that particular gas. The reason is that with the increase in the temperature, there is decrease in the density because of expansion, volume expansion or cubical expansion of the gas. And consequently, the speed of the sound increases. A general formula for calculating speed of sound in a gas because of change in temperature is given by V. That means V stands for speed of sound at 0 degrees Celsius plus 0.61 T, where T stands for the temperature. The speed of sound in air increases by about 0.61 meter per second or 61 centimeter per second for each degree rise in temperature, and that is why the factor 0.61 has been added over here. So if the speed of sound is directly proportional to the square root of the absolute temperature, this means that the sound would travel faster on a hot summer day than on a cold winter day. The third factor that affects the speed of sound in a gas is the humidity present in the medium. The presence of water vapor in the air or in the gas changes the density of that particular medium. And the presence of water vapor reduces, in fact, the density of the air or the gas. And we already know the lesser the density of the gas, the faster is the speed of sound. And therefore, sound travels faster on a rainy day than on a dry day. Or we can say that because density of the moist air is less than density of the dry air, therefore the speed of sound in moist air is greater than speed of sound in the dry air. And now let us move on to the last factor which affects the speed of sound in a gas. And that is the direction of the wind. The speed of sound is affected by the speed of wind because wind drifts the air or gas along its direction of motion. If the wind blows in the same direction in which the sound is traveling, then the speed of sound increases, and then the formula to calculate speed of sound becomes speed of sound in still air. Still air means when there is no wind, plus speed of the wind. But if the wind blows in the opposite direction in which the sound travels, then the speed of the sound decreases, and it is given by speed of the sound in still air minus speed of the wind. So these were the 4 factors on which speed of sound in a gas depend upon. Let us now see the factors that do not affect the speed of sound in a gas. And the first one is the pressure of the gas. The speed of sound is independent of the pressure of the gas. When pressure increases, the volume of the gas decreases, but the mass of the gas remains the same, which means that for that particular volume, the density of the gas will increase by the same amount as the pressure has increased, and therefore the ratio pressure upon density, that means I'm talking about this ratio pressure upon density, will remain the same because they will cancel each other's effect. For example, if the pressure of the gas is doubled, then the volume will become half. And for constant mass, the density is also doubled. So this way, the ratio remains the same. Also, there is no effect of amplitude, wavelength, or frequency on the speed of sound. And you have seen this clearly in one of the previous videos where I have shown you in some of the simulation that the change in frequency, wavelength, or amplitude does not affect the speed of sound. All vibrations cause sound, but the human ear cannot hear the sound of all frequencies. When the frequency of vibration of a body, that is frequency of sound, which is between 20 Hz to 20,000 Hz, then sound can be heard by us. We cannot hear sound of frequencies below 20 Hz and above 20,000 Hz. So the range of frequency of human is from 20 Hz to 20,000 Hz, and this frequency range is known as sonic frequency, and this is the audible limit for the humans. The sound of frequency lower than 20 Hz are known as infrasonic waves. The earthquakes, volcanic eruptions, simple pendulum, elephants produce infrasonic sound. But sounds of frequencies higher than 20 Hz, 20 kilohertz, that means 20,000 Hz, are known as ultrasonic waves. We will now study more about ultrasonic waves. Because of the high frequency, ultrasounds have some of the very special properties which audible sound does not have. Ultrasound waves have very high frequency, due to which they have very high penetrating power. And this has got many applications in our day-to-day life, which we will see just now. Second is that ultrasound has very high energy associated with it. A wave carries energy with it. We all know this. But due to high frequency, an ultrasound has very high amount of energy. Then, when a low frequency sound meets an obstacle, it easily bends round the corners and spread in all the directions. But ultrasounds are able to travel along a well-defined straight path, even in the presence of obstacle. This means they do not bend appreciably at the edges of the obstacle. And these are some properties which make ultrasonic sound waves very useful for us. Ultrasonic
devices are the devices which use ultrasonic waves or frequencies. So these devices are used to detect objects and measure distances. This technique of using ultrasonic waves, which is known as ultrasound imaging or sonography, is often used in medicine field. Industrial use of ultrasound is that it is used for cleaning, mixing, and accelerating chemical processes. Animals such as bats use ultrasound to locate their prey and obstacle, and this method is also known as echolocation. They use the technique of echo to locate their prey. Dolphins also hear ultrasound and use such sound in their navigational system to orient and capture prey. At the same time, another ultrasound application is an automatic door opener. Ultrasound testing is used to find flaws in materials and to measure thickness of the objects. One of the very common use of ultrasound is in underwater range finding. As I've told you just now, that ultrasound have very high frequency, so their penetration power is very good at the sea level, below the sea level, and therefore this technique is used in sonar. Ultrasonic cleaners are used at frequencies from 20 to 40 kilohertz, that means 20,000 hertz to 40,000 hertz, for jewelry, lenses, and other optical parts, watches, dental instruments, and surgical instruments. Apart from these mentioned applications, there are still many other applications of ultrasound frequencies or ultrasonic frequencies uh, in various other fields. This particular chart tells you the approximate frequency ranges corresponding to ultrasound with a rough guide of some applications. Infrasonic or infrasound below 20 Hz. Acoustic, that means the audible range, which is between 20 Hz to 20,000 Hz. And ultrasound is beyond 20,000 Hz. So the ultrasound frequencies between 20,000 Hz to 2 megahertz are used by animals in chemical field, medicinal, and for destructive purpose also. However, beyond 2 megahertz, it is used for diagnostic and NDE purposes.